Welcome to the master class of traceability and information flow. By the end of this module, you will be able to master the following. You will be able to explain why traditional one step up and one step down traceability fails in real incidents. Also, you will be able to understand the concept of information velocity and why speed matters more than data volume. Also, you will be able to identify where information delay occurs in your supply chain. And also, you will be able to distinguish between having records and having visibility. And also, you will be able to design faster, clearer information flow in your own system. And finally, you will be able to implement practical traceability improvements whether you are a small farm or a global manufacturer. All right, so let's get into it. We'll just have a quick highlight of our community to whom this course is designed for, but definitely it's applicable across all the sectors and they can tailor it to their own. But primarily it's for our sector of primary industry and food manufacturing, starting with farmers and primary producers. This course is for you, and it's also for food and ingredient manufacturers. It's for multinational food companies and for small scale processors. This course is designed for all of you, and also for distributor and distribution and service sector, including cold storage and logistics providers, importers, and it's also for exporters. This course is designed for you and is also for retailers and supermarkets. It's designed for food service and catering chains. And also, this course is designed for professional specialists, including food safety managers and quality assurance teams, for internal and third party auditors. And this course also is designed for food consultants and for technical specialists. And finally, this course is designed for governance and oversights, including regulatory professionals, NGO and public officials, public health officials, supply chain risk managers, and also is designed for senior uh, leadership teams. Our design principle, as always, we say we design every module and every slide that it must make sense to both a small farm and a global corporation because we speak a universal language of food safety. Let's get into it. The core truth today that you are going to learn is that you cannot control what you cannot see in time. And definitely, you know this truth. Now, in food safety, system resilience is measured by one thing only, and that is the speed at which critical information reaches decision makers. All right? And we will elaborate. Now, visibility is your ability to see what is happening, right? And once you see what's happening, you will be able to stop it before harm is spread. Okay? That is the traceability in essence. Is the ability to see what's happening, especially the hazards or risk, and be able to stop it before the risk or the harm is spread. That's the core truth. Now, why traceability fails, especially one step up and one step down traceability, why it breaks? Well, most regulations require knowing your immediate supplier and immediate customer. And by knowing those and being able to connect them, that means, according to those regulations, that you fulfill the requirement. And that create the compliance, but not true visibility that we are going to learn here today. Because when a hazard is discovered, this outdated approach of one step up and one step down, actually, it forces you to do the following. First, to contact one party at a time and also wait for their records and repeat the process at each step. and manually reconstruct the entire chain. And by the time you have answers, the effective, the affected product has moved further, and that increasing risk and potential harm. As you can see here visually, if you look at one step up and one step down approach, it means you have supplier and you have customer and your company in between, and that's the end of the traceability. But if you look at end-to-end traceability, it goes two tiers up and two tiers down, which means you track the origin, for example, from the farm, the harvesting, all right, the processing there in the farm, all the way until the consumer, not the retailer, all the way until the consumer. And you track, you break down all the process one by one, which we are going to learn now. That is the end-to-end traceability, which is the visibility. All right. You will be able to see everything clearly. Now, let's explore first why traceability fail, and let's examine records versus visibility. If you look at having records, primarily it means that data exists somewhere and it requires most of the time manual retrieval, and those data or records are fragmented across parties, and the approach here is reactive only, because only once something happened you go there to look for those records, so that's reactive. And mainly the most part is only compliance focus. It's when the authorities ask you to trace back the records, then you go and look for them. Or when something happened, you go and look for those records to fulfill the compliance. So that is having record. But having visibility means that the data is accessible now. And that's what we are going to learn today together. That means the data is accessible now and it's automated and connected. And also it's integrated across supply chain, and it enables you to have a proactive decision, and also it facilitates harm reduction, and it focuses on eliminating the harm, not the compliant focus. That is the visibility. All right. That is where we are going to focus. And definitely we will demonstrate the traditional way, and we will always do that, and then demonstrate the best practices along this course. Now, information that exists is not the same as information that moves. You agree with me? And I will prove it to you shortly. Now, let's look at the information velocity here. The missing concept in food safety is the information velocity. Okay? Now, traceability is not about data completeness. It is about information velocity, the speed at which critical information reaches the people who must act. All right? That is the traceability. It's not about data completeness. It's about information velocity. All right? Now, in a recall scenario, every recall scenario, every hour of delay is equivalent to exponential harm. That means the more you delay, the more the harm grows. Also, in recall scenario, real life, every manual handoffs is equivalent to compounding risk. And we will elaborate now with real world example. And also in recall scenario in real life, every missing link is equivalent to wider contamination. All right? And don't worry, let me demonstrate that with a real world example. Now, let's assume it is Tuesday, 9 a.m. A retail store in Germany reports suspected salmonella in packed chicken. All right, let's examine the slow system here, the manual record first. In a slow system or the manual record, in this scenario, when the retail store called at 9 a.m. to report a suspected salmonella in packed chicken, the following will happen in slow system manual records. At 9 a.m., typically, this is what will happen, okay? At 9 a.m., a store calls distributor and leaves voicemail. Then at 11 a.m., distributor takes paper records and identifies suppliers. Then at 2 p.m., distributor calls processor and requests batch number or batch information. And on Wednesday, that's the following day now. On Wednesday, 10 a.m., the processor locates production records and identifies 3 farms. Then on Wednesday, now again the following day, at 3 p.m., the processor contacts farms for delivery dates. And on Thursday, the next day, now it has been 2 days, right? On Thursday, the farm records, the farm records are being received, and then the cross reference was done manually. And on Friday, affected product was finally identified. This is 5 days later. And the results, because of this, you have 12,000 units already consumed across 6 countries. All right. This is the slow manual handling of the traceability. Now, let's examine the fast system, the integrated digital. All right. It goes as following. Same scenario. At 9 a.m., a store scans product barcode and uploads to the system. Then at 9:02 a.m., system traces production batch number PB4429 specific. And then at 9:03 a.m., system identifies 3 source farms and exact delivery dates. And at 9:05 a.m., system locates all 847 units from same batch. And at 9:10 a.m., automated alerts sent to all affected retailers. And at 9:30 a.m., products pulled from shelves. The results here, only 23 units are consumed and outbreak is contained. You have the same hazards, same supply chain, but different information velocity and different outcomes. So you can see now traceability in real sense means the information velocity. And you can see the difference that it made. Now, your traceability system, and you have to note this, your traceability system is only as good as it is its slowest information pathways. All right? Your traceability system is only as good as it is its slowest information pathway. And this is the visual for what we just demonstrated in a slow information flow. The branching path increase contamination, all right, and hazard spread slowly, then accelerates. But in fast information, the contamination, uh, containment will limits the harm because it's fast, and rapid detection and alert will limit the containment of the harm. Now, the purpose clarity here, traceability exists to contain harm, all right? Not to reconstruct history. Traceability systems are often designed for post-incident investigation as following: what went wrong, who was responsible, and what can we learn? Okay? This is how typically the traceability is designed for post-incident investigation. This is important, but it's secondary, okay? It's important to know what went wrong and who is responsible and what can we learn. But it's secondary. The primary purpose of the traceability is harm containment. All right? There's a difference now. Traceability primary purpose is not post-incident investigation. The primary purpose is harm containment, which means to identify affected product immediately and locate it precisely and stop it before consumption and minimize exposure, right? To contain the harm. That's the purpose of traceability, the primary purpose. Designing your system for speed first to contain the harm. Make sure that's what you do. Design a system for speed first to contain the harm, and then later on, the forensics would be the second. All right, that's the secondary. Let's look at the operational excellence with real incident and the cause of delay. Now, if we look at the real world impact, slow versus fast traceability. Now, if you look at before the slow traceability, you will see the hazard is detected in 1 day, supplier contacted in day 3, records retrieved in day 5, and affected lots identified at 8, and recall initiated in day 10, and product consumes in 847, and illness reported at 3, and the cause was the cost direct cost is 4.2 million USD plus brand damage. That's the slow traceability that from the example we demonstrated earlier. But if we look at after or the fast traceability, when we demonstrated the fast traceability, you have seen that the hazard was detected in the first hour. The system query was done in first hour, and the affected lots identified was in second hour. A recall initiated in 4 hour, and product consumed more like 12 units, right, or 23 units we mentioned earlier, and the illness reported is zero, and the cost of containment is $180,000. Right now, the difference here, an integrated system that connects data in real time, not days, and that's what you need. All right. This is also the visual for the slow traceability and the fast traceability. Okay. Now, let's look at the fundamental challenge here. Product moves continuously, and information must keep the pace, right? Physical goods flow through your supply chain every day. That means receiving, transformation, like processing, all right, and shipping and distribution. If your information system cannot track this movement in real time, you have the following. You have visibility of the past, not the present. You have records, not traceability. And you have compliance, not control. All right? Because the true traceability must have continuous receiving or continuous information in real time to keep up with the continuous movement. All right? Now, where traceability breaks, let's examine that. Transformation points is where visibility breaks. When the product change form is where the visibility disappear. All right. Visibility is simple when product identity stays constant. For example, you receive a pallet of apples from the farm, it's packed, it's palletized, it's tested, you have the certificate, and you conduct your test, and the pallet stays the same. And then you take that pallet and you store it the same way. You don't change anything. And then you receive the order and you ship the same pallet, and the customer receive the same pallet. That's easy to track. All right. Same palette, same identity, and easy to track. Now, but traceability breaks at transformation. Okay? Example, let's look at the sauce manufacturing. Let's start with the input. In sauce manufacturing, inputs on Monday morning, they have tomato lot number A2401 with 500 kg, and also they have tomato lot number A2402 with 500 kg, and they have the other input, the third input is a spice mix, lot number B7733 50 kg. Fourth input, garlic lot number C1156 25 kg, and salt lot number D9983 10 kg. The process after the input, all ingredients are mixed in production batch number PB8847. And then the output on Monday afternoon, all these inputs were in the morning. Now the output in the afternoon, just give me a second. The output on Monday afternoon, first output, 2,400 bottles of sauce from mixing all of above inputs. Then these 2,400 bottles of sauce are packed into 200 cases. And then those 200 cases are labeled, like each case is labeled. They start from SC8847 001, start with the first case, all the way until case number 200 labels SC 8847 200 in sequence. All right. Now, the critical question here, if garlic, the garlic that which has lot number C-1156, if this garlic lot is later found to be contaminated, which finished cases are affected here? All right. Now, without lot genealogy tracking through transformation, you cannot answer this question fast enough. All right. Without lot genealogy tracking through transformation, you will not be able to answer this question fast enough, because you won't know where that mix went. And that means you must recall all the 200 cases, or worse, you will be recalling all the production from the week if you don't have, you don't know where that lot was mixed today or yesterday or, tomorrow. Now, but with the proper tracking, you know instantly that all cases from SC 8847 001 through SC 8847 200 contain the affected garlic lot. All right, the 200 cases. All right. Now, if you look at lot genealogy, the broken genealogy versus the maintained genealogy. All right. The maintained genealogy, you have a specific output are linked to specific inputs, and individual lots are tracked, and each input is identified and linked. But if you look at the broken genealogy where you don't have a specific date, you don't know where a specific date went to which is specific date, all right, then the ingredients are mixed and input lots combined in one batch, for example, BP8847, and traceability lot is unknown. Finished product cases if not tracked, and you might end up, like we said, called all production from the week being recalled. Now we will go through explaining how to do it right. Okay, so let's just take it slow. Now, the regulatory context here. How does regulatory context affects the traceability, and why compliance doesn't equate to effective traceability? Many regulations, all right, around the world, including some sections of the US FDA, Food Safety Modernization Act, or FSMA, and the European Union's General Food Law, EC 178 of 2002, they established a fundamental requirement, and that fundamental requirements require you to have one step back and one step forward, right? One S, one F visibility. This establishes a baseline for accountability, which is good. It's for the baseline, okay? However, compliance with the minimum standards does not guarantee speed of information retrievals, does not guarantee visibility across multiple tiers of the supply chain, and does not guarantee ability to make critical stop decisions in hours, not days. Okay? Effective traceability goes beyond regulatory minimum to enable rapid harm containment and protect consumers and brands. That is the effective traceability. It goes beyond regulatory minimums, enable rapid harm containment, and protect consumers and brands. If you see at the regulatory minimum, it has a limited scope, one step up, one step forward, one step back, okay? And it's audit focused mainly. It fulfills the requirement of audit. But the operational excellence requires end-to-end traceability and rapid crisis response. Now let's examine the traceability for decisions. If your traceability system cannot support a stop decision, it's not a true traceability. We have learned in Module 7, which established that clear authority is meaningless without timely information, right? We learned that in Module 7. Your traceability system must answer 3 questions within hour, not days. All right? The first question that it must answer is what is affected, which means which specific lot, specific batch, or specific units contain hazard. That must be answered within hours. And also, how much product is involved. Okay? Second question, where is it now? This question also must be answered within hours, if not less than hours. Must be answered, which means you must answer that is your product still in the warehouse? You must know that. Is it in transit to customers? The system must know that. And is it already at retail locations? The system must show that. Or is it potentially consumed? Also, you must answer that within hours. The third question is who has it? Effective traceability also answers this question. Who has it? All right? Who has your product? Which customers received affected products? And which distributions centers? And which retail stores? All these questions. We will learn together now how, if you don't have it already, we will learn together how to design the system. Answer all these questions under 15 to under 1 hour, ranging between 15 minutes to 1 hour. Now, also, can we stop it before consumption? This question must be answered. Is there time to intercept? You must know that clearly. The system must know that clearly. And can we issue effective, effective consumer warning? Or what is the exposure window? All these questions must be answered through effective traceability design. Now let's examine traditional uh, practice and versus best practice for the traceability. The traditional approach, which is a manual investigations, happen as following. The quality manager, for example, discovers an issue. So the quality manager calls production supervisor and say, which lot did we use yesterday? And the supervisor will check the paper book log and say, let me call you back. 2 hours later, the supervisor will come back with the answer and say we use lot number, for example, A-2401 and A-2402, 2402, and B-7733. That's after 2 hours, the supervisor will come back with that. And then the quality manager will call the warehouse and say, where did these lots go? And the warehouse will check shipping manifests manually. And 4 hours later, partial list of customers will be identified and still unknown which specific products, exact quantities, and current locations. And the total time to get incomplete answers here will take 6 to 8 hours. But if we look at best traceability practices with integrated systems, it goes like this. Same scenario, but now it's different. Quality manager scans product barcode or enters lot code. Then the system instantly display all input lots used in production and all finished products created from these lots and current location of every unit, including in the warehouse, in transit or delivered, and customer list with contact information and quantities at each location. The total time to get complete answers will take 2 to 5 minutes. So let's see now how to implement this with 4 weeks action plan, okay? To implement such system where you can be able to scan your barcode or enter a lot number and get all this information under 2 to 5 minutes. This is how you can implement effective traceability in 4 weeks action plan. Week one, assess current capabilities. All right. First, conduct a mock trace exercise. Then pick one finished product lot from last week. Then time, how long it takes to answer the 4 critical questions that we demonstrated above. Then document every delay, every phone call, and every manual lookup, and also identify your slowest information pathway. Then in week two, map critical data points. That means you should list every point where product change, form, or location and identify what data must be captured at each point and determine where data currently live, either on paper, in a spreadsheet, or system, and find gaps where information is lost or delayed. That's in week two. In week three, design quick wins by starting with one critical pathway. For example, raw material to finished product. Then implement simple digital capture. Even a shared spreadsheet is better than paper. Then create large genealogy links where the mixing happen, which inputs match with output, which inputs match which outputs. Create large genealogy links. Then test with another mark trace. That's in week three. Then in week four, expand and automate. Add barcode scanning if not already in place. Connect your internal system from receipt, production to shipping, and train staff on why speed matter, not just how to enter data, but why speed and traceability matter. And then set targets to answer all questions in under 4 hours. All the four questions that we examine above there. All right. Now, this is the visual demonstration with what we just talk about to identify choice and assess the evidence and time check and decide or pause. All right. Because authority without information also cause paralysis. Now, if your system requires days of manual investigation, answer these questions, the four questions that we examined there. You have records, not decisions, enabling traceability, right? If you just go back and examine those questions, four questions, if your system cannot answer them, you can agree with me that you only have records and you don't have decision enabling traceability. But always start simple. Okay, small operations can achieve decision enabling traceability with basic tools. The key here is connecting the data, okay, not the perfection. Now, let's look at the effective traceability together and design it. What good traceability actually looks like is end-to-end visibility, okay? And the three-question tests to examine end-to-end visibility, your system can answer these questions instantly if it has end-to-end visibility. First question, for traceback, where did these ingredients come from? That should name suppliers, farm, and lot. Third question, to trace within, okay? What products contains these ingredients lot? The finished goods affected with this lot. Third question is trace forward. Where are these products now? Are they in the warehouse, in transit, in retail, or consumed? All right. You must have instant data. Your system must answer this instantly. That ensure you have end-to-end visibility. Let's examine now traditional versus best practices with real examples. Example one, small dairy cooperative with 50 farmers in Kenya, for example. The traditional practice here, farmers deliver milk in unmarked containers, and cooperative records total volume received per day in ledger. And milk from all farms are mixed immediately, and if contamination found, they cannot identify the source farm, and they must discard the entire day's production for all the farms now, in case they found Now let's see the best practice, how it can be done better instead of mixing and receiving without identifications and just discard everything together. Evidently, you in your mind now you already have the idea of the best practice. First, each farmer must have the unique ID number. Let's assume now this cooperative implemented the best practice. So what they did, they ensured each farmer has unique ID number and milk is weighed and sampled at collection and then stacked with farmer's ID plus date. And the simple spreadsheet tracker has been implemented that include farmer ID, collection date, volume, tank number, the numbers, the tanks also. So now in a small Excel or any document spreadsheet, farmer ID, collection date, volume, and tank number. And then the finished products are labeled with production date plus tank number. Because in a tank number here, they have all this information. All right. So the finished product is labeled with production date plus tank number. And if contamination is found, they can now easily trace it back to the specific farm within 30 minutes, right? And only affected batches will be discarded and other farms will be protected. Not like first, where everything will just be discarded because it's mixed without identification. The tools you need here to implement this best practice is just number tags and scale and basic spreadsheets and printed labels. All right, you can implement that best practice, and it can cost under $500 to implement. All right, the time to implement this all can be done under 2 weeks. Now let's examine another example, and this now is a let's say a mid-sized food processor, and this is a sauce manufacturing in Vietnam. The traditional practices that are in place in this mid-sized food processor source in Vietnam, they have ingredient received and then lot codes are written in notebook and then the production batch numbers are assigned and recorded on whiteboard and then finished cases are labeled with production dates only. And if ingredient recall, they must check notebook and cross-reference with whiteboard and cannot determine which finished cases contains affected ingredients, and they must recall the entire week's production to be safe. This is the traditional practice. Now let's say they implemented best practice. So they will do the following. First ingredients received, and lot codes is scanned into the system. Then the production batch is created in system and linked to ingredient lots used, and system generates batch with the specific numbers. For example, batch number PB8847 contains tomato A-2401 and garlic C-1156 and spicy batch number B-7733 with specifics. And now the finished cases are labeled with batch number plus barcode. And if garlic C-1156 is recalled, as we demonstrated earlier, the system instantly shows all batches that are using that lot. And the precise recall here only affected cases with minimal waste, and they don't need to recall the entire week for to stay safe. The tools needed to implement such practices in a mid-size manufacturer is just a barcode scanner that will cost around $200 and basic inventory software that could cost around $50 a month for subscription and label printer that costs under or around $300 and totally will cost under $1,000 plus 600 for software subscription annually, right? The time to implement this around 4 to 6 weeks, you can complete that. Example three, large multi-site manufacturer, global distribution. Okay, let's say they are also having traditional practices. So for traceability. So if we see here in their traditional practices for traceability, they have the following. First, each facility uses different software systems and distribution centers track shipments separately, and customer delivery dates is in sales system. If recall needed, they must contact each facility individually, and manual compilation of data from multiple sources, and it takes between 24 to 48 hours to get complete picture. Now, let's assume they implement best practices for traceability. They will do the following. Have integrated ERP system across all facilities and real-time visibility from production to warehousing to distribution to retails. And they have API connection with major retail partners. And if recall needed, a single query shows global production locations and automated customer notifications is generated and complete picture in under 1 hour, including, compared to the 24 to 48 hours, they can do it now under 1 hour. And the tools needed here, they need enterprise traceability platforms and system integration. But the cost here for this um, is between 50,000 to 500,000, depending on the scales. And this is a multinational company. The time to implement will take around 6 to 12 hours. Now, let's look at the critical tracking event here, ECTs, what to capture with critical tracking events or ECTs. First, capture receiving, okay? And that includes supplier's name and location, product and ingredients descriptions, lot and batch code from suppliers, quantity and unit of measures, date and time received, and storage location assigned. Those are receiving. Capture that. And then capture the transformation or the production of the ingredients. That should include or must include production batch number, all input slots used, the ingredient genealogy here, and quantities of each inputs, and date and time of the production, and equipment used, and operator and shifts. Also capture the packing. That must include finished product lots and batch codes, and link to production batch and quantity package and packaging size and format and date and time of packing. Then you must capture the shipping. Very important here. That must include customer name and then delivery address, production lots, batch shipping, and quantities per lot, and date and time ship and the transport details. The key elements, KDs, key elements KD is minimum information required. Here, for every critical tracking event, record the following. First, unique identifier, lot card, batch number, and serial number. Okay. Secondly, record the quantity, how much, with unit in kg or in cases or liters or others measures. And then record the timestamp, when it happened, the date plus time, and record the location where it happened and was it, and link what it came from and what it became. Okay. Now, the ultimate test here, Can you trace forward and backward through your entire chain in minutes? Not days, minutes. Can you do? Try this exercise. You might do it, okay? First, pick a finished product from last week, then set a timer, then answer what raw material are in it and track back, all right? And then answer where are all units from that production run now, okay? From that production run, where are the units now? And trace forward also. And if you can do this in under 15 minutes, you have effective traceability. But if it takes hours or days, you have records, not traceability, and you can improve that. We will show you how to improve it here. And this is how effective traceability should look like. From tier to supplier, you must have the information include lot codes and quantities and timestamp and supplier tier one. You must have the information regarding received events, location, link to source. And then in your facility, all the information include transformation or processing or mixing and batch links and timestamp. And then you move forward to distribution, packing, shipping, location, and quantities. And you move further to retail, to consumer also with final lot and sale and timestamp and track query and trace query. Okay. Now, let's look at the implementation reality. People protect production before systems protect people. All right? Even the most advanced traceability system fail if people don't use it correctly. And here are real scenarios with practical solutions we will go through now. The first scenario, the time pressure. Let's look at the real life. So what happened here with the real life time pressure? Production line running at full speed. Scanning each pallet takes 30 seconds. So the supervisor say, just write it down. All right, just write it down. We will scan it later during the break. By the end of the shift, handwriting notes are illegible for scanning and data never entered. Now the traceability here is broken. And why this happened? Why this complication happened is because the system slows down the production. That's a fact. And workers are measured on output, not data accuracies. That's another fact. And then no immediate consequences also for skipping the scan. That's another reality. Those three reality came together and it led to traceability broken down. Now, how to fix this? First, the traditional approach to fix this is as following. You post signs, you must scan every pallet. Well, that doesn't work actually. And discipline workers who skip scanning. That's also traditional and doesn't work. The results here, workers will scan when the supervisor is watching, and they will skip it when not. It's just you must scan. Okay, so but let's here do the best practices, fix that with best practices that actually work. First, redesign the workflow. This is what we learned in previous modules, the system design. Okay. Always look into the system. Redesign the workflow and place the scanner at the point where pallet is already stacked. For example, at wrapper before forklift pick or something, just don't let it slow down the work. And then make it faster also. Use auto scan gates or RFID that don't require stopping. Thirdly, change the incentive also. The production count only registers after scan. And no scan means no credit for production. And then provide immediate feedback. How? If the screen shows pallet 47 records lot number, for example, A-2401, so worker knows it works. So you put there the immediate feedback visibly. All right. Now, let's look at the implementation step, how you can fix this immediately with 5 steps. One, time your current process. You need to figure that out first. How long does the scanning actually add? Then identify natural stop point in your workflow. Don't let it slow the work down. Break it. Figure it out along the workflow. Find the natural stop point there. Thirdly, move your scanning to these points, not an extra step, but the natural steps. So you don't need to add extra work. Just add it to the natural stop points. And then number four, test with workers. Just ask simple questions such as, is this faster or slower than writing it down? And you can figure that out and then adjust until scanning is the path of the least resistance. As simple as that, you can implement it. Now let's look at scenario two, the system distrust. That was a time pressure. And now you see how to implement it. Now let's look at the system distrust and we will examine the traditional approach and then the best practice. We will implement the best practice for traceability. First, what happened? Workers scan ingredient lot code and system shows lot not found in database. So workers think, hmm, system is wrong again. I'll just use yesterday's lot code. It's close enough anyways. And they did that. Now the result, the finished product is linked to wrong ingredient lot. So the traceability here is corrupt. The system distrust. And why did this happen? It's because first, the receiving department didn't enter new lot into the system. Secondly, the system has history of repeated errors. So the workers think maybe it's the system. Thirdly, workers has no way to fix the problem also because there is no communication channel designed there to escalate or to to figure it out. Then the production also cannot for data issues, okay? Because they are incentivized for volume also. Now, how to fix this? First, let's look at the traditional way that doesn't work. Usually, you tell the workers never override the system. That doesn't work. Or the results here will be the production will stop and the supervisor will override anyway. They cannot stop the production. So what should you do? The actual best practices are the following. First, fix the root cause. Receiving department must interlock before releasing to production. Secondly, create workaround protocol. Okay, also align with the reality here. Create workaround protocol. If lot not found, workers will scan new lot barcode and enter to the system, and the system will create temporary entry. System after creating the temporary entry, the system will flag it to the receiving department, complete the recording. You see? And then make it visible. Place a dashboard that shows all the temporary entry and receiving team must clear them daily and then build trust. Okay, build trust. When systems say lot not found, just make it a training. When systems say lot not found, it is because lot truly wasn't found and the receiving is not received yet, not a system error. So train the team to build the trust. The implementation steps to do all that. First, audit your current data entry. Where do lots enter the system. Secondly, create rule. No physical product release until data entry. Thirdly, design a temporary entry workflow for exception. And fourth, train workers. If system says no found, it means receiving hasn't logged it yet. And here is what to do. You see? Here is what to do. And you show them what to do. And you document it and you hang it there. And they will see it every day. When they see not found, they'll say, oh, wow, this is because of this, and this is what I need to do. Then finally, track and fix. Review all temporary entries weekly and identify patterns and fix them. Let's look at third scenario, the production priority, the pressure of production. Okay? Now, what happened? Quality manager discovers a potential issue mid-production run. Wow. Then the production manager says, we cannot stop now. We will lose 4 hours of production. So let's finish this batch first and we will investigate later, please. That's what the production manager said. Now, the result here, as the quality agreed, the result here potentially affected product continues to be made and shipped, and traceability data exists, but action is delayed. Happen most cases, right? The pressure of production. Now, why this happen? First, the production manager is measured on output and efficiency. Secondly, the quality manager has no authority to stop the production from system design. Okay? He hasn't been given authority to stop the production, and cost of stopping is visible and immediate, of course. We will lose 4 hours. That's immediately visible. But the cost of not stopping is invisible and future. The recall, the penalties, the reputational damage, the regulatory scrutiny, all these are invisible, but they are costs of not stopping, cost of not stopping in the future. Now, how to fix this? First, the traditional approach that doesn't work is to give quality manager authority to stop production. That doesn't work. Okay. The results here because the production manager pressures quality manager and they will create conflict because quality will have authority to stop it and production is under pressure to produce the value that will create conflict. All right. It will create conflict. We don't need conflict. We always want to create the best work environment. That's why we need to design the system for it. So let's look at the best practices here, which actually work. First, change the decision framework. All right. System design. Change this decision framework. Create clear, stop or investigate or continue criteria. What we learned in previous modules. Design the system. Create clear criteria. If this happen, you can stop. If this happen, you should investigate. If this happen, you should continue. Clear. Create that. Then secondly, make it objective. All right. If X happen, then stop. If Y happen, then segregate and investigate. If Z happen, then continue with enhanced monitoring. Clearly like that. SOPs, CCPs, OPRPs, right? All that. Just check the previous modules to how to design system thinking. Now, thirdly, remove the personal conflict. Remove the personal conflict. What do? The decision is based on criteria. It's not on personalities anymore. Even the production manager will say, you know what? X happened, so I need to stop. Z happened, so we can continue with enhanced monitoring, like that. So now you don't have personal conflict anymore, and always teamwork and collaboration are the best. So we designed the system for it. Now, fourth, change the incentive. The production manager is measured now on the good product produced, not only the total product produced, the good product and total product, right? Priority for good product for food safety. And then make stopping easy. Pre-plan the investigation mode that doesn't fully stop the line. Just segregate outputs. All right. And this is how you can implement it in 5 steps also. First, define your stop criteria. Very important here. What triggers immediate halt versus the investigation? All right. Then create decision tree. Quality issues, if quality, for example, if quality issues detected, then check severity and then follow the protocol. Segregate, investigate, hold. Yes, clear decision tree. Laminate it and put it there and train people on it. Talk about it in toolbox talks. Your training, competence assessment. All right. Then train both production and quality team on the same criteria and practice with the scenario. Very important here. Scenario. Always practice with scenario. Implement with scenario. If we find X, what do? We investigate. If we find Z, we stop. If we find Y, like that, okay? So then measure and reward. Track issues caught and controlled as a positive metrics. Issues caught and contained. Track that and reward that as a positive metrics. Now, let's look at design principles for real world success. First, make data capture faster than manual workaround. Make data capture faster than workaround. If scanning is slower than writing, workers will write, okay? So make capture, data capture, make it faster than manual workaround. This is the first design principle for real world success in traceability. Solution here is to integrate scanning into existing workflow. Secondly, build trust through system accuracy and reliability. If system is often wrong, workers will ignore it. Solution here is to fix data quality at the source. And you can do that. Third principle, empower people. Stop production when traceability is compromised. Tell them they have the power to stop when the traceability is compromised. We are protecting the consumers here. We are protecting the public. Food safety is a public good. You know that. This is a public good. Obligation, responsibility. If stopping has only negative consequences, it won't happen, right? So the solution here is to create clear criteria and remove personal conflict. Reward instead. Reward those who caught the problem and stop the production. And the final principle is to train on why traceability matter, not just how to use the system. If workers don't understand the purpose, they will skip under pressure. The solution is to show real example of how traceability prevented harm. All right. and sometimes to demonstrate also of what happened in similar scenarios when there was no traceability. Demonstrate that the real world data, protect the customer, protect the consumer, protect the company, protect the workers, protect the system, creates food safety, safe environment. Now, you have the ideal process is to have seamless integration and accurate real-time data capture where data capture is faster than manual workaround, as we said. And then you have actual workaround, human behavior under pressure, often leads to system bypass and make the traceability, the breaks the and break the traceability, the behavior and pressure, right? What happened? That's the actual workaround. Now, let's look beyond crisis now. Beyond crisis response. Let's see the other good things that traceability does for the business. Traceability as a strategic tool for operational excellence. All right? Most organizations view traceability as a reactive tool for recall and investigation. Advanced organizations, however, use traceability proactively for continuous improvement, for cost reduction, and for risk prevention. You know that you can use traceability for continuous improvement, for risk prevention, and for cost reduction. Now, let's look at the traditional and best practices for traceability here. Proactive application. Application one, quality improvement and root cause analysis. The traditional approach here, which is reactive, we will see this. Because customer complaints about product defect, quality team investigates corrective actions and cannot determine when problem started and cannot identify which supplier lots correlate with defects and implement blanket change, hoping to fix issues and wait to see if complaints increase. The best practice, which means being proactive, is to do the following. First, traceability system tracks quality metrics by supplier lot, and patterns are detected. Defects correlate with suppliers A's lot from farms X, and system also flags farm X lots have 12% higher defects rate. So quality team investigate farm X specifically and root cause found, harvesting equipment issue, and problem solved at source. The defect rate dropped to zero. That's the proactive best practice. Great example. If we look at coffee roaster in Colombia, they tracked capping scores by farm lot over 6 months. Okay, proactive now. Proactive. First, they tracked capping scores by farm lot over 6 months, and they discovered lots from farms at elevation of above 1,800 meter scored consistently higher. So, they adjusted sourcing strategically to prioritize high elevation farms, and the premium product line created as a result, with 23% price increase justified by quality data. And farmers at high elevation received better price and incentivized on quality. That's the proactive implementation. The tools needed to implement such here is quality tracking integrated with lot code and basic data analysis only. Cost minimal. You can use existing traceability data, and the time to implement this just within 2 to 4 weeks. Set up the tracking. Let's look at the second application of the traceability strategically, which is waste reduction and inventory optimization. The traditional approach here, which is reactive, will do the following: integrate expiries in warehouse, discovered during physical inventory count, and cannot determine why it wasn't used, and cannot identify if patterns exists, and write off as loss or order replacement. Well, the best practices here, being a proactive, this is how you can use the traceability to reduce the waste. First, the system tracks ingredients, lot and age, and use patterns. Automated alerts. Lot number B-7733 expires in 7 days. 50 kg unused. The production scheduler prioritizes using that lot, and the system suggests used in batch number BP-8850 scheduled for tomorrow. An ingredient use before expiration, and now you have zero waste. Let's implement with a real example. A bakery chain in Germany has 12 locations. They implemented FIFO, first in, first out, tracking by lot. The system automatically suggests oldest lot for production, and waste from expired ingredients reduced by 67%. Okay? The annual saving here is 47,000 euros. And improved freshness. Product now use ingredients within 3 days of receipt versus 14 days previously. The tools needed here: inventory management with expiration tracking and automated alert. Cost around 2,000 to 5,000 euros for mid-size operations. Time to implement between 4 to 6 weeks only. Now let's examine that application. Supplier performance management. Traceability is used strategically for supplier performance management. These are another use for traceability here. The traditional approach here will be reactive as following. Supplier delivers poor quality batch, rejects the batch and requests replacement, and no systematic tracking of supplier performance, and cannot identify patterns across suppliers, and supplier selection is based on price and relationships, not data. But the best practices here to use the sustainability to improve proactively here. First, the system tracks metrics by supplier, such as on-time delivery, quality acceptance rate, and lot consistency. Then, the dashboard is implemented to show, for example, supplier A has 98% acceptance, and supplier B has 87% acceptance. And then the quarterly supplier review based on objective data is implemented, and high performers are rewarded with larger orders, and low performers are given improvement targets or replaced. All right. Now let's demonstrate with real example. Seafood processor in Thailand. They tracked 15 fishing vessels over 12 months. The metrics here, including temperature compliance, parasite detection rates, and size consistency. They discovered 3 vessels had over 95% compliance, and 12 vessels averaged at 78%. So they shifted 60% of volume to top performing vessels, and the quality complaints reduced by 41% at this point. As a result, and the top vessels received premium pricing, incentivized for best practices. The tools needed here, so included supplier scorecards linked to lot acceptance data, and the cost minimal. You can use existing receiving data, all right? And the time to implement between 2 to 3 weeks to set up the dashboard. Now, Let's look at the application 4 of the traceability strategically. Use traceability for predictive risk prevention. First, the traditional approach here for risk prevention is in a reactive way will look like first, regulatory alert issued about contamination risk in a specific region, and you scramble to determine if you source from that region, and you have manual review of supplier records, and you are uncertain if current inventory is affected. But the best practices be proactive and implement sustainability for risk, predictive risk inventory, risk prevention. You will do the following. First, you do traceability, you implement traceability systems that includes geographic origin data, and regulatory alert is received, for example, the listeria risk in region X. So the system queries instantly show you have 3 lots from region X in inventory, and the system shows you the lots that have been identified: A-2405, A-2407, A-2411. And the finished products using those lots have been identified too, and voluntary hold have been placed now before regulatory requirements. As a result, and testing is conducted and product is cleared or removed. That's the best practice. The real world example here, let's look at the spice importer in Netherlands. Integrated supplier geographic data into traceability system. An aflatoxin alert is issued for a specific growing region in India. So the system query took 30 seconds and showed 2 lots are affected, both still in the warehouse. The lots are quarantined and tested before use. One lot is failed the test and destroyed before entering production. And now you have zero finished product is affected and zero recall cost. And regulatory compliance demonstrated proactively. The tools needed here: geographic origin tracking alert monitoring system. No, geographic origin tracking alert and uh, geographic origin tracking and alert monitoring system. The cost here between $1,000 to $3,000 for alert integration, and the time to implement that is between 2 to 4 weeks. All right. Now, this is how to implement proactive traceability. In 6 week plan, week 1 to week 2, identify your opportunity. First, review the last 12 months and figure what problems repeated there. Then calculate costs, including waste, cost of waste, cost of rework, cost of customer complaints, and cost of issues, supplier issues. Then prioritize which problem has highest cost or frequency. Then define metrics. What would you track to prevent this? All right? All this between 1 to 2 weeks. Then move to week 3 to week 4. Enhance data capture by doing the following. First, determine what additional data is needed here. Do you need quality score? Do you need geographic origin? Or which type of data do you need? Then modify receiving and production processes to capture this data. Then link new data to existing lot codes and test data captured for 1 week. All right. Then you move to week 5 to build analysis capability by doing the following. First, create simple dashboard or report and set up automated alerts for key thresholds and train team to interpret data and establish review frequency. Is it daily, weekly, or monthly? You can establish that. And then in week 6, act on the insights by doing the following. First, run first analysis cycle and identify patterns or outliers and take corrective actions and measure the impact and refine and expand. That's how you do it. Easy, right? You can do it. The strategic values here, when traceability is fast and accurate, it becomes a continuous improvement engine, not just crisis tools. All right? Now, organizations that use traceability proactively do the following. They reduce waste by 40 to 70%, and they improve supplier quality by 25 to 50%, and they prevent incidents before they occur, and they make data driven decisions instead of reactive guesses. Okay? And they build competitive advantage through operational excellence. And you have seen all, we have demonstrated each point above there, right? Now, the key principle here, the same data you need for recall can drive daily operational improvements if you design your system to make that data accessible and actionable, right? Now, the traceability is not merely a mechanism for finding problems. It is a strategic enabler for understanding your entire operational ecosystem, allowing you to proactively prevent issues, optimize processes, and build a more resilient and trusted supplier chain. All right? Let's look at the strategic insight here, right? Uh, Now, let's explore the proactive system versus the reactive system. In Module 6 and Module 7, and also here in Module 8, together they address a fundamental challenge in food safety. Most systems are designed to learn from failure by doing the following. Incident occurs, investigation reveals what went wrong, okay? And then the corrective actions is implemented and system improvement is done, and then wait for the next incident to test the improvements. That's what most systems are designed to learn from failure. This is reactive management. You improve by failing. That's reactive management. Effective systems are designed to prevent failures by doing the following. Hazards are identified before they cause harm. And you can learn that in Module 6, right? The risk based thinking module. We detail how to design a risk based thinking system. And also, effective systems are designed to prevent failure through clear authority, which enable immediate actions. And we demonstrate that in Module 7, the decision making process and design. And also, effective systems are designed to prevent failures through fast information, which enables precise decisions. And that is what we taught in Module 8 here, traceability. Now, the integration, how Module 6, Module 7, and 8 work together. Module 6 taught us risk assessment, right? You know what could go wrong, right? Identifies potential hazards before they occur and prioritizes risk based on likelihood and severity and establishes preventive controls. And then in Module 7, the decision authority. We learned that in Module 7. Know who can stop the process, right? Who can stop it? By defining clear decision making authority and removes barrier to immediate actions and empowers people act without delay. Then in Module 8 here, traceability, you know where it is, where your product is, and how to stop it fast, where the hazard, where the risk is. Know how to stop it fast by providing real-time visibility of product location and enable precise identification of affected products and support rapid containment decisions. Together, they make a system that contains harm before it reaches consumer. Let's look at traditional versus integrated approach with real scenarios. First scenario, potential allergen cross-contamination is detected. The traditional approach, if modules are working in silos, the following happen. Day 1 at 10 a.m., production supervisor noticed almond residues on equipment is scheduled for almond-free production. Supervisor is unsure at this point if this is a stop production issues and calls quality manager. But quality manager is not available, he's in a meeting. So the supervisor continues the production while waiting for the guidelines from the quality manager who is in the meeting. And then at 2 p.m., 4 hours later, the quality manager calls back the same day and decides the production should have been stopped. Quality manager says, but 4 hours of product has already been produced, and now they must determine is it safe or must it be destroyed? Through this day, day 1 to day 2, the investigation begins. And which batch were affected, and where did those batches go, and manual review of production logs and keeping records 24 hours, compile complete information. Then in day 3, the decision is made. Recall 6 batches, over inclusive to be safe. All 6 batches must be recalled. And customer notification is sent, and the cost here is $45,000 in this destroyed product plus recall logistics. Although 2 batches were eventually safe, but recalled anyway and destroyed anyway, over inclusive to be safe. That's the traditional when modules are working in silos. Now, let's look at integrated approach when modules, what we learn in module 6 and what we learn in module 7, and here in module 8 are working together. Same scenario. Day 1, 10 a.m., production supervisor notices almond residues on equipment scheduled for almond-free product, but supervisor learned in module 6, the risk assessment in action. So the supervisor is trained on allergen cross-contamination as a high risk. So supervisor has clear criteria. This is a high risk, and any visible allergen residues means to stop the production immediately. So the supervisor he knows this is a stop worthy issues and stops the production. In module 7, Also, the supervisor was taught the decision authority in action. Supervisor has authority to stop production immediately and no need to wait for quality manager approval. So the production stopped at 10:05 a.m. 5 minutes of production made, not 4 hours, as that traditional where modules were working in silos. And now module 8 traceability also have been taught to the supervisor and the whole team. Let's look at it in action. The supervisor scans batch code of 5 minute production run from 10 a.m. to 10:05 a.m. And the system shows specific batch number PB-8851 and 47 units are produced in 5 minutes. So the system shows all 47 units is still in production area, not yet shipped. And the quality manager is notified automatically while in the meeting and reviews remotely. At 11 a.m., the decision is made 1 hour later. The 47 quarantined and tested. The testing shows allergen present above threshold and 47 units are destroyed. And equipment is cleaned and verified at this point, and the production resumed at 2 p.m. The outcome here, the cost is $380 in destroyed product, 47 units, versus the 6 batches that were destroyed in the traditional way, and no customer impact. The product never left facility, and no recall, and the saving of $44,620 that was destroyed in traditional way. Now, how to implement the integrated approach here? Do the following. Step 1, map your critical decisions point from week 1 to week 2. Identify scenario, okay, identify scenarios where module 6, 7, and 8 must work together. Just give me a second. I have some presentation glitch here. Mm, 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 mm. Now, how to implement the integrated approach? Step 1, map your critical decision points. We want to do identify scenario where module 6, 7, and 8 must work together. First, identify allergen cross-contamination. Uh, the first, okay. Uh, Step 1, map critical decision points. Week 1 to 2, identify scenarios where module 6, 7 and work together. For example, allergen cross-contamination is detected and foreign materials found in product and temperature deviation during storage. Scenario 4, supplier quality issues discovered, equipment malfunction during production, another scenario, and pathogen test positive results, another scenario. And then for each scenario, document the following. What is the hazard? And you can learn that in module 6. And who has authority to stop? That's module 7. And what information is needed to decide? That's what you learned today in module 8. Step 2, create decision protocol, week 3 to week 4. For each critical scenario, create a one-page protocol. For example, allergen cross-contamination protocol goes like this. If allergen residues visible on equipment or allergen detected in wrong products, then stop production immediately. And who can stop the production? any production supervisor or quality staff. That's what Module 8 taught, decision authority. And information needed, you can relate to Module 8 here, include what batch was being produced, how much was made before stopping, and where is that product now, and has it been shipped, or where is it? And then the decision there, including product is still in facility, for example, plus not yet packed, either to destroy or clean equipment and resume, right? Retest, destroy, clean equipment, resume. If the product is packed but not shipped, quarantine, test, and decide. If product is already shipped, then initiate immediate recall protocol. The authority levels here, supervisor can stop the production, quality manager can authorize destruction of up to $5,000 value of the product, a plant manager can authorize destruction of a product value above 5,000 to 50,000, and VP operations required for destruction of above 50,000 or customer recall. Step 3, train on integration. All right, that's week 5. Don't train modules separately, train scenarios. Training exercise. For example, you are the production supervisor, you notice, and then you insert the scenario, what to do here, and walk through. 1, recognize the hazard, module 6 knowledge. Secondly, know your authority, module 7 clarity. And thirdly, access the information, module 8 system. And fifth, make decisions. Fourth, make decisions. And fifth, execute the action. Practice with real scenario until response become automatic. Then step 4, test with simulation. Week 6 and ongoing, conduct unannounced drills. First, by inject simulated issues. For example, so say these ingredients launch this failed test, and you continue with the scenario, and then observe, does the team follow the protocol, and then measure how long to stop, how long to identify effective products, and how long to decide. And then debrief what worked and what didn't, and then improve, update protocols based on learning. Target performance here, recognize recognition to stop, from recognition to stopping, recognition of the hazard to stopping the product should be under 5 minutes, and from stop to information gathered should be under 15 minutes, and from information to decision should be under 30 minutes, and the total incidents to containment should be under 1 hour. The strategic outcome, when module 6, 7, and 8 are integrated, the strategic outcome are the following. Hazards are recognized immediately, train awareness, and action is taken without delay, clear authority, and decisions are precise, fast information, and harm is contained before it reaches consumers. This is the difference between a reactive organization that learn from failure and proactive organization that prevent them. All right? Now, let's look at how to implement, how to build effective sustainability. This is a guided approach. Step 1, map your chain. The traditional approach that don't work look like the following. It creates complex workflow charts. The traditional approach that doesn't work look like following. It creates complex flow charts with every possible details and spend months documenting everything and get overwhelmed and never finish. The results, no actionable map and no progress. But the best practice that actually works look like following. Start simple. Draw your main product flow on one page. Mark only the critical points from receiving to production to packing to shipping and identify where information currently get lost or delayed. The time needed here is just between a day and two, not months. Real example. Let's assume a small honey producer in Kenya. They drew a simple flow from beekeepers to collections to filtering to bottling to distribution. They have identified that there is no record of which beekeeper supplied which batch. So the solution, they implemented numbered collection containers in a simple logbook that cost them around $50 for containers and logbook. The time needed here is just 1 week to implement. All right. Now let's demonstrate with a real example in a mid-sized bakery in France. They mapped from flour receipt to mixing to baking, packing, delivery. They identified gaps. They found that they couldn't link finished bread to flour lots used. The solutions, production batch sheets linking ingredient lot to inputs was implemented. Cost here for template creation is free, and the training only took 2 hours, and the time for implementations only 2 weeks to implement. Now, the following is the implementation checklist. First, draw your product flow, that's 1 page maximum, and mark transformation points where products change forms, and mark handoff points where ownership or locations change. Then identify current delays. Where do you lose visibility? Then prioritize which gap poses the biggest risk. That's the implementation checklist. All right. Now, then step two, identify critical tracking events, CTs. Traditional approach that don't work look like the following. They try to track everything at every step and create 50 field data entry forms, and workers are overwhelmed and they skip data entry, and the results is incomplete data and system failure. But the best practice that actually works look like following. Identify minimum data needed for traceability, focus on moments that matters like receiving and transformation and shipping of the product, and keep data entry simple and fast, and expand only after basic works. To demonstrate that with real world example, fish processing plant in Thailand. What they track? Minimum. They track receiving, they have vessel ID and catch date and species and weight and ice temperature. And for processing, they track processing batch number, vessel lot used, and output quantity. And freezing, they track batch number, freezer location, and freeze date. And for shipping, they they track customer and batch numbers shipped and quantity and dates. What they don't track, what they don't track, which is nice to have, but not criticals, are the following: individual fish weight, exact processing times, worker's name, and details weather conditions. Those are nice to have, but they are not critical. Now, the results here, they can trace any finished product to source vessel in under 5 minutes. Real example is Spice Blending Company in India. The critical tracking events first, raw spice recipe, suppliers, the origin country, lot code, and arrival date. And also the blending, they track blend batch number, input lot code used, quantities, and blend date. Thirdly, the packing, they track packing lot code, blend batch used, and packing date. And for shipping, they track customer, packing lots shipped, quantity, and ship dates. The data captured here, 8 fields per event, not 50. And time to record, 2 minutes per batch, not 20 minutes. Compliance, 100% data entry because it's simple. And the following is the implementation checklist. First, list every point where product change or move. And for each point, ask, what must I know to trace forward and backward? Then eliminate nice to have data fields and test. Can workers complete data entry in under 3 minutes? And if no, keep simplifying further. Now, step 3, design for speed. Traditional approach that don't work does the following. Buy expensive software first, try to automate everything immediately, system too complex and workers can use it, and fall back to manual processes. And the results is wasted investment and no improvement at all. But the best practice that actually works looks like the following. Start with simplest tool that works. Automate only the slowest manual steps and build trust before adding complexity and scale up gradually. Progression examples. Level 1, paper base, a small farm in Uganda, cassava, right? The tool used here just numbered harvest bag versus logbook. The process, each bag is tagged with farm section plus date. Processing records which bag went into which batch, and it costs only around $20. The speed here, they can trace batch to farm section in 10 minutes. When to upgrade? Only when manual lookup takes under 30 minutes regularly. Level 2, spreadsheet base. Here in cooperative in payroll for coffee, the tool used here is shared Excel sheet process. Each farmer delivers recorded Each farmer delivery is recorded with ID, dates, weight, and quality score. The roasting batches link to farmer ID used and cost $0 because they use existing computer. And the speed here, they can trace roasted batch to source farmers in 5 minutes. And when to upgrade here? Only when multiple people need simultaneous access. Level 3, basic software. Here, let's give example of processor in Philippines for coconut oil. The tool used here is just simple inventory software, subscription of $50 per month. The process here is a barcode scanning at receiving, production, and shipping, and automatic lot genealogy tracking, and it costs around 200. The cost here, they buy a scanner for $200 plus $600 for per year for software subscription, which is 50 per month. And the speed here, they can trace any product to source in 2 minutes. So when can they upgrade here? Only when expanding to multiple facilities. If we look at level 4, integrated system, For example, here, a manufacturer in Brazil, meat manufacturer. The tool here, they use enterprise ERP with traceability model. Uh, the process here include RFID tags, automated data capture, and real-time visibility. Integration with supplier and customer systems, and costs here over 100,000 USD for initial investment, and speed they can trace globally in under 1 minute. When can they upgrade? Only when operating across countries or across continents. The key principle here is start where you are. Perfect is the enemy of good, okay? The implementation checklist, assess current state. Is it paper, spreadsheet, or software? Then identify slowest manual step. That's the biggest time waster. And then implement one improvement. For example, add barcode to receiving. Thirdly, test for 2 weeks. Then measure. Did it actually save time? And then, if yes, expand. And if no, keep adjusting. Then we move now to step 4, test with mock recall. The traditional approach to test with mock recall, which doesn't work, look like following. Announce mock recall in advance, give team time to prepare, everyone performs perfectly, and declare success. And real recall happen when it happened, the system fail. Now, the best practice here, which actually works, look like following. And announce mock recalls, realistic scenarios, measure actual performance, identify real gaps, fix and test again. And for the mock recall protocol here, the preparation is done once. Just select 5 random finished products from last month and record their lot codes privately. Then schedule an announced test. Don't tell the team when. And the execution will take around 30 to 60 minutes. First, announce mock recall is starting now, just as you are there. And then give them the production lot code and start the timer. The team must answer the following. What raw materials are in the products? Track back. And where are all units from this lot now? Trace forward. And who are the affected customers? The team must answer these 3 questions. Then stop the timer when complete answers are provided, and verify accuracy of the answers. The scoring happen based on the following. You score excellence if complete accurate answers is done under 15 minutes, and you give a score of good if complete accurate answers is given between 15 to 60 minutes, and you score need improvement if the answer is in between 1 and 4 hours. And also you can score system failure if they cannot provide complete answers in 4 hours. Real example, let's say a dairy cooperative in New Zealand, for example. The first mock recall before the improvement, the following happened. Time to track back to farms took 6 hours, and time to locate finished product took 8 hours, and accuracy was 70% with missed some locations. The grade here, system failure. And then the actions taken are the following. They implemented barcode scanning at milk location and created digital batch sheets linking farms to products and train staff on system. The second mock recall after the improvement, the following happened. Time to track back to farms, 12 minutes. Time to locate finished products took 18 minutes. and accuracy is 100%, and the grade here is an excellent. Now, the following is the implementation sheet. First, conduct first mock recall, establish the baseline, then document time taken and gaps found, then prioritize top 3 gaps to fix, then implement improvements, then test again in 4 to 6 weeks, then repeat quarterly. All right. Traceability maturity ladder from basic to intermediate to advanced. The traceability maturity ladder from basic level, there is a manual records paper logbook and one-step traceability, immediate suppliers and customers, and trace time is between 4 to 24 hours and suitable. This is suitable, the basic level for small farms or single location operations, and it costs under $500. An example for that would be a vegetable farmer with harvest log. For intermediate levels, you have the following. You have digital records, spreadsheets or basic software, and internal end-to-end visibility, and trace time is between an hour and 4 hours. And this is suitable, the intermediate level is suitable for processors or small manufacturers, and the cost is around $1,000 to $10,000. Example for that would be sauce manufacturer with batch tracking. Then you have advanced level, which has the following. It has integrated system such as ERP or traceability platform, and supply chain visibility includes suppliers and customers, and trace time is between 15 minutes to an hour. And this is suitable for multi-sites manufacturers or exporters, and it might cost between $10,000 to $100,000. Example for seafood exporter with global distribution. But the world-class level has the following: real-time connected system, end-to-end supply chain integration. Trace time is done under 15 minutes, and this is suitable for global brands and high-risk products. The cost here is over $100,000. Example is infant formula manufacturers. Final guides. Is that simple? Okay. A small operation can achieve effective traceability with basic tools. The key is connecting the data. The key is connecting the data, not perfecting it. Here is your 30 days action plan. In week 1, map your chain and identify gaps. In week 2, identify minimum data to capture. In week 3, implement one improvement. And in week 4, conduct mock recall and measure the results. Right? Success metrics. Can you answer what's in it, what's in your product, and where is it? And under 1 hour, can you do that? That's the measure for success metrics. If yes, you have functional traceability. And now work on it faster, okay? Work on making it faster. If you can answer all this under 1 hour, you have traceability. Just improve it to make it faster. Final reframing. Traceability is not about knowing what happened in the past. It is about stopping what is happening in time. You now understand that why traditional one step up and one step down traceability fails. The concept of information, you also understand now the concept of information velocity. Speed matters more than volumes, all right? And also you understand now where visibility breaks, transformation points, and manual handoffs. And also you understand what effective traceability looks like CTEs, KDEs, and end-to-end visibility, and how to implement it in your context, map, identity, design, and test, and why people and process matter as much as technology. Your next action, conduct a mock recall this week. Time how long it took to answer the following questions. What raw materials are in the finished products? Where are all finished products from these production run? The time tells you everything about your current capability. Next module, module 9, will address verification, validation, and continuous learning. Ensure your system worked as intended and improve over time. Thank you and see you in module 9.